The Earth has two principal motions. There's revolution, where you're going around the sun, and it's like the Earth going around the sun to make one complete trip around. It's 365 and a fourth days. That's why we have leap year added in there. Rotation is where you're spinning on your axis, and that's a 24-hour cycle. Technically, it's less than 24 hours, but to make a 24-hour clock, you got to round up. You can't have it be in between. So it's technically a little bit less, but you spin on your axis a little less than 24 hours. Now, that spinning on your axis, we actually wobble. So we don't spin in a nice smooth pattern. Think about a top, like those old-fashioned toys where you spin, and eventually when it starts to slow down a little bit, you have a little bit of a wobble to it. And the Earth has that same idea. And that wobble will change the axis of the Earth over an extremely long period of time, and it's not something you necessarily see in your own lifetime. But we toggle back and forth from being 23.5 degrees to minus 23.5 degrees, which is interesting because if we ever get straight up and down where we don't have a tilt and we don't have any seasons, because that's what we're going to learn here is the reason you have seasons is the fact that you have a tilt of your axis and that you actually revolve around the sun. So you have a 23.5 degree tilt and we revolve around the sun. That creates the seasons. So if you have it straight up and down, so if you're doing the precession and you're halfway in between, then you don't have any seasons. It's just the same all year round wherever you're at. There's no change, like here in the Midwest where we get that nice change and we have spring, summer, fall, and a winter. You just wouldn't have that. It would just be the same all year round. Now, looking at revolution, our Earth's orbit is a squashed circle, if you will, which is called an ellipse. And it was discovered by Johannes Kepler. And when he discovered this, it made all the math work out, which is why we know that we are an elliptical orbit, or not, and the sun's not in the complete center of it. It's kind of off to the side a little bit. So that does make us closer to the sun during, technically it's during our winter time, and then we're further from the sun in the northern hemisphere summertime. When you're closer to the sun, it's called perihelion, and perihelion is roughly sometime around January 4th-ish, depending on leap year and stuff, but somewhere around that 3rd, 4th, 5th time frame, and that's during the northern hemisphere's winter. And that means we're roughly 91 million miles from the sun. When it comes aphelion, which is sometime around July 4th, then we are furthest from the sun, and it's 94 million miles away, which is why you always hear the average 93 million miles from the sun, because that's the average in between the two. And the fact that we're in an ellipse, we go around the sun every 365.24266 days, which means that it's not a perfect calendar, which hence why you have to have a leap year. And even having that, after so many decades, you have to go through and adjust it again, because it does still get off a little bit, because obviously it's not exactly 0.24. So you still get off, so your calendar has to be changed in order to keep up with it. Now when you're looking at the reasons for the seasons, I said the tilt. Don't forget, it's the tilt, tilt, tilt. Got to have that some type of tilt going on, where you're basically changing the sun's rays, like the intensity of the rays through a revolution. But you also have to revolve, otherwise you wouldn't have seasons. If you just stayed in one spot and you had a tilt, it still wouldn't make a difference. You've got to actually move around your light source. So those are the two reasons. You've got the tilt and the revolution for your reasons for your seasons. Now, with that tilt means you have a change in the temperatures. Here's a nice map that shows general temperatures for January. Obviously they're very averaged, and it's for the whole globe, and you can see in the northern hemisphere it's typically colder. All the purples and blues means it's colder, because it's winter in the northern hemisphere and it's summer going on in the southern hemisphere. When you flip on to July, you can see there's the switch, where it's warmer in the northern hemisphere because that's our summertime, and then in the southern hemisphere it's colder, Now there isn't much of a difference, you can see. It doesn't have a huge swing in temperatures from their summer to their winter in the southern hemisphere. As you look at the northern hemisphere, cold, pockets of some of those purple, and then when you get to the summer, complete switch where it's a lot warmer, and that's because there's more land mass. Land heats up and cools down faster, and to a higher temperature and to a lower temperature than water does. And there's obviously a lot more water in the southern hemisphere, so that would be why their temperatures don't seem to have that huge swing from a summer to a winter. Now your seasons, summer solstice, winter solstice, you get your spring and autumnal equinoxes going on, and there's the dates that they typically happen. And it's a little bit different depending on where you're at in your orbit and that kind of thing, but they're somewhere around those dates. What I like about this is it shows the pictures for each season, so top one's spring, summer, fall, and winter. And look at the differences of how the sunlight strikes the earth. I mean, that's a good sign, indication right there of just here's how the tilt of the earth changes the sun's intensity rays over the earth. So whenever you're at one of the equinoxes, so the top and the bottom picture right underneath each other, here you can see that that in equinoxes you have 12 hours a day, 12 hours a night equal across the earth, and you can see that. When you get over here to the summer one, you have a little bit more showing of where the intensity of the rays are. There's more illuminated in the northern hemisphere, and you can see cut across right where you see that little dot, kind of where the equator is. You can see the North Pole has light, whereas the South Pole does not. If you look at the winter one, the North Pole does not have any light, but the South Pole has light. And that shows you that the intensity of the rays here in our summertime, northern hemisphere summertime, are up here in the northern hemisphere. Whereas if you look at the winter one, seeing how you're not getting any light at all at the North Pole, then most of the sun's intensity is down in the southern hemisphere. So it's just a really neat picture that really kind of shows that change in where the intensity of the rays are, which makes the big difference. Here's looking at the curvature of the earth. You have the sun's rays coming in. In this case, the earth is tilted away from the sun, so that southern hemisphere is picking up more direct sun rays. The more direct sun rays means your temperatures are going to be warmer, which is what's going on right now. Obviously, we're getting close to an equinox, about halfway there, and the northern hemisphere has colder temperatures going on because the sun's intensity is less, because most of the sun's rays, the more direct rays, meaning 90 degrees straight coming down, is in the southern hemisphere. And another way to look at it here's somewhere near the equator. So this would be a good example of an equinox. You got the sun's rays coming straight down, most intense. You get that 90-degree angle, and you get your most intense rays. Somewhere halfway in between here in the poles, so roughly somewhere in the Kansas City area would be a good example for that. Then you have that same amount of sunlight coming in, and you spread it over a larger area. So you're just reducing the intensity. When you get up towards the polar region, same amount comes in, but you really spread it over even a larger area, and you can make it less and less intense. The same idea as looking at flashlights, shine the flashlight straight down, more intense, you start to tilt it, the intensity decreases quite a bit. And that will make a big difference in your temperatures. Now the fact that you are further away versus closer to the sun, yes, you can get more intense radiation the closer you are to the sun, but it's not enough to make dramatic temperature differences that would create seasonal changes. Seasons are caused by the tilt of the earth and the fact that we go around the sun. So keep that in mind.